All right. Good afternoon, everyone, and welcome to Intro to Space Navigation Spring 2025, Lecture 24. And today we'll be finishing up our discussion of horizon-based optical navigation. So as a refresher, in the last lecture, we talked about this method of navigation where if you have a camera on your spacecraft and you take a photo of the Earth or the Moon, and this also works for other planets, as long as it can be modeled as a triaxial ellipsoid, you're good. This method will work. It tends to struggle if, for example, you're working with an oblong kind of asteroid shape, or maybe you're looking at like Phobos or Deimos or some non-spherical moon of some other planet, right? But if your thing is roughly a sphere, or like the Earth, it's an oblate spheroid, you can use this method. And the very basic idea is detect the circle in the image. Center gives you direction, size gives you distance. Direction and distance is position, you're done. That's the very, very high level idea of how we do horizon-based OpNav. It's a little bit more complicated than that. And what we started to do last lecture is build up this mathematical theory. We talked about the tightly bounding cone around a planet of we've got these directions in an image, and we know that those directions are related to some matrix which describes information about the shape of the body that we're navigating with respect to, and our position, our translation and rotation with respect to that body. And we made some progress down that direction, but we're not quite done yet. And we kind of stopped cold in the middle of some math. So apologies for that. But I would like to wrap up with that. And in what I hope is a relatively short lecture today, might not even need to take a break partway through. Maybe we could just go straight through the notes. You should have everything that you need to code up your own horizon-based OpNav and do homework 6. So without further ado, we'll get into horizon-based OpNav part 2. Right. So the first thing I want to discuss is how to parameterize a conic in an image. So we've been talking about a conic as this kind of 3D triaxial ellipsoid described as some matrix, like the planet shape matrix. But what we measure in the image is not necessarily the planet. It's kind of like a projection of the planet into an image. Here's a good idea here. This is an image conic, and then this is a triaxial ellipsoid. Right now we're talking about parameterizing an conic in an image. So in general, a generic conic section is described by ax squared plus bxy plus cy squared plus dx plus fy plus g equals 0. And so this is any conic section. We have an ellipse when b squared minus 4ac is less than 0, and a circle when a minus c squared plus b squared equals 0. Okay, and so let's see. Okay, so you get the idea. X and Y would be points in 2D space, and A, B, C, D, F, G are going to be 6 parameters that describe that generic conic section. And then a point is on that conic section if ax squared plus bxy plus cy squared plus dx plus fy plus g evaluates to 0. And if it's not 0, then you're either inside or outside the conic. That's the idea. So we can take this equation and write it in matrix form if we introduce homogeneous coordinates again. So if I say that x as a homogeneous vector is x, y, and then 1, then we can say that x transpose c x is, we've got a b over 2, d over 2, b over 2, c, f over 2, d over 2, f over 2, and g. Where here I'm using the letter c in this case to mean this is a matrix. Over here it's a scalar in the matrix. Don't get confused. So moving forward, unless I specify, I'm talking about this c. Don't get confused. So we're going to be focusing on the planet shape matrix, or the kind of image conic shape matrix, capital C. And C is a full rank symmetric matrix that describes the conic in the image plane. So we can compute the cone formed by back projection of an image conic. So we talked about this tightly bounding cone here. We have the image conic, or we can find the image conic through image processing. We want this tightly bounding cone. We can compute the cone formed by back projection of the image conic. Okay. So first, we introduce the matrix P, capital P, from A to B. This is going to be a partial homogeneous matrix. So it's going to be the direction cosine matrix from the A frame to the B frame, and the translation from A to B. And this, so you can imagine this is the homogeneous matrix that we saw back up here, right, where we're just cutting off the 0, 0, 0, and then 1. And by this definition, if we go from C to C, well, this would just be the identity, 3 by 3, because you're not doing a rotation, and 0, 3 by 1, because you're not doing a translation. So the cone is, remember, pi is our tightly bounding cone, is proportional to P from C to C times the large matrix C, P from C to C. Or we could just put it this way. The C matrix and then zeros is proportional to this MC matrix from last class, and then zeros. So C, the image conic, is proportional to MC, and we said that MC was AC, RC, RC transpose AC minus RC transpose AC RC minus 1 times AC. So all we've done is we've established that this matrix C is proportional to this guy. So the conic of the planet or the moon in the image is mathematically equal to a scaled form of this tightly bounding cone. So this might seem like common sense. You might have said, like, Professor, I could have told you from this diagram that this image conic and this traxial ellipsoid tightly bounding cone, that these were going to be similar. There's going to be scaled forms of the same construct. Now we have the mathematical background to prove it. So that's all we've established here. Okay, so moving on, our goal is trying to find R given some equation, which we still haven't quite set up yet, but we're almost there. So the next subtopic is horizon-based position estimation. So we know that an image conic obeys the constraint X transpose CX equals 0. And we know that C is proportional to this MC. Okay. So if we put this together, we could say that X transpose, and then we have AC, RC, RC transpose AC minus RC, AC, RC minus 1, AC, X hat equals 0. Okay, this is our major checkpoint, right? We finally have our observations and our state in the same equation. I'll write that down. Finally have, after 2 lectures, I mean, I guess we could have fit this into 1 lecture, but we finally have our measurements and our state in the same equation. So now just solve. Well, sadly, it's not quite so simple. I've actually still got about 2 pages of math on how to solve this. But you get the idea here. AC is in theory something that we know, right? Because AC was formed from AP, right? Let's see, where did we describe this? Yeah, we said that AC is really AP and then some direction cosine matrices. But then even further back, we said that AP just comes from the long, short, and then medium axes of our triaxial ellipsoid. In theory, you could look those up if it was the Earth or the Moon or Mars, so on and so forth. So we can look up AP. We're assuming that we know our rotation, T from C to P. So AC is something that we know going in. And then X is something that we directly measure in the image. That's the line of sight direction. That's basically one of these points in our image, one of these red points here, which are on this image conic. So what we want to do is find a way to take this equation and solve it for RC. Right? So let's see here. Moving forward, just mention this. Next, solve for RC. Since AC is symmetric, it can be factorized into AC is equal to B transpose B. Okay, where now we can say X transpose is B transpose B RC RC transpose B minus RC B transpose B RC minus 1. Sorry, I started to close my parentheses, and so 1, and then B transpose B. X hat equals 0. Oh, excuse me. Sorry about that. All right. So what we can do, we can say, all right, we appear to have a B transpose and a B kind of sandwiching everything that's going on in here, especially if we kind of break things up. So first of all, here we have BRC. Here we have BRC transpose. And then here is a, oh, apologies. This should be a transpose, and this should be a transpose. So here we have, again, BRC and BRC. Okay. And let's see, if we pull out some common terms here, we get X transpose, B transpose. And then in parentheses, we get this BRC, and then BRC transpose minus, and then we have BRC transpose, BRC minus 1, and then this would just be times the identity matrix, and then we have BX equals 0. Okay, so now what we're going to do is we're going to define, you'll notice we've kind of grouped this BRC appears in here 4 times. And we also have this BX that appears on the outside. So it's almost like a scaled form of what we were talking about before. So we will define, again, we don't really know what B is. We just know that B transpose B is AC. So it can be found by factorization. Let's say that X hat prime is BX hat. I guess this needs a little triangle if it's defined as. And then similarly, RC prime is defined as BRC. Our equation gets a little bit simpler then. Now we have X hat prime transpose. And then we have RC prime transpose minus, and then in parentheses, we have RC prime transpose, RC prime minus 1 times the identity matrix, and then we have X hat prime equals 0. Okay. So what we have now, say this equation describes the problem of navigating relative to a unit sphere. Okay. So imagine if we went back up to this equation here, the one that I'm starring right now. We'll say, imagine if the planet shape matrix became the identity in the star equation. We would just have what we have here. We've basically done away with the planet shape matrix by doing this factorization that we've talked about. So now I think we should probably go back and talk about where B comes from, because we kind of just shoehorned that in there. But you can see how we've basically turned a harder math problem into an easier math problem, where now we are navigating relative to a unit sphere. And as long as we keep track of what B is, we can always work backwards and find the real RC instead of RC prime. But it's going to be a lot easier to solve for RC prime. Okay, so recall that AC is B transpose B, and that AC is T planet to camera, A in the planet frame, T camera to planet. And remember that A in the planet frame is 1 over A squared, 1 over B squared, 1 over C squared, zeros on the off diagonal. Right, it's all from last class. So we can also say that AP is some new matrix we're introducing, D. It's D transpose D, where D is even easier. It's just 1 over A, 1 over B, 1 over C. So you see how if we have this matrix, we transpose it, which accomplishes nothing, and then multiply it by itself, we're back to AP. Okay. The reason we do that is because now we can say that AC is, okay, attitude transformation matrix from planet to camera, and then making a substitution, we get D transpose D, and then attitude transformation matrix from camera to planet. And if you look at that, this sure looks like B transpose, and then this sure looks like B. Okay, so therefore, this matrix B, which is crucial in simplifying our equation from kind of the generic case to the unit sphere case, B is just this kind of modified form of the planet shape matrix and our rotation, T from camera to planet. Okay. So now if we can go back and solve this equation here, which I guess I'll do double star. If we can solve the double star equation, we're done. Okay. We have these x prime, well, I guess we don't, but we have our line of sight directions in the image, and we can multiply those by B to get x hat prime. And we can set up this equation, and then we can solve for RC prime, and that's kind of what we need to discuss next. But if we have RC prime, then we can go backwards and find what B is. So if we know what B is, then we can go from RC prime to RC, and that's it. That is the location of the planet in the image frame, which includes that all-important distance as well as direction, which is very, very crucial. So we can see how the next step is just how to solve the double star equation we've discussed here. But I want to pause for a knowledge check. Any questions on this? So far, so good? If it seems like a lot, that's fine. As we go through, and when we get to the end, I'm going to put a little like summary chart where it's like, by the way, these are the actual steps that you need to code up. Because I realize as I'm going through a derivation, it can be tough to tell like, which of these do I need to code up and which of these are just neat mathematically? And it will be clear at the end. So stay tuned. All right. Next is how to navigate relative to a unit sphere. So the problem is something like this, and I'm not even going to try to draw a circle. I fully admit that Microsoft can do that better than me. So imagine that you've got an observer at some point out here, and really what we're after is this vector, which actually I kind of drew in a straight line. That's pretty good. Oh, let's just do that. There we go. But we don't measure the center of the planet. What we measure is some point which is tangent to its surface, right? Something like this. Yeah, let me try that one more time. No, it's a good thing I'm not a perfectionist. Okay, there we go. And so this is tangent to the surface. So we'll say that this is a right angle. And also, because we said this is a unit sphere, this has to be a distance of 1. Okay. So we're going to define this angle as phi prime. And we're going to define, so this vector is our r prime, and then this measurement here is our x hat prime. Maybe this is the ith x hat prime. So I guess that would also make this be phi I, the idea here. So for the ith point on the edge of the planet, you're going to have this kind of setup. And we have a triangle here, so we can start using some trig functions. So let's say that the sine of phi, and be clear that that's phi, prime, you remember SOHCAHTOA, sine is opposite over hypotenuse, so it's going to be 1 over the norm of r prime. Okay. Similarly, cosine of phi prime, okay, cosine is adjacent over hypotenuse. What this is going to end up being is xi prime hat projected onto r prime and divided by both their norms. So this is really just, if we take the dot product of these two vectors, right, we get this phi. So this is xi prime, and then this is the norm of r prime. Okay. And we will also define, we're just kind of getting all of our characters introduced before we go to the next phase of our derivation. I'm going to introduce this new term si hat prime. And all this is our line of sight direction normalized. But this is, of course, our transformed line of sight direction. So it's still prime. But we take the image line of sight direction, transform it by multiplying it by b, and then normalize it. That gives us s. So while it might seem unfamiliar, s is still something that pops right out of our image. And we have these equations for phi. And we can start to combine some of these terms here. So we'll say that the cosine of phi, well, that's the same thing as just saying that it is si prime transpose. And then we've got r vec divided by the norm. So all we did was we took this equation and we just said, well, this part is s, so we'll just make a substitution. That's all we did. Okay. Now what we can do is we can divide both sides of the equation by the cosine of phi prime. So we end up with just the number 1 is equal to si prime transpose. And then over here we have this r prime divided by the norm of r prime, and then the cosine of phi prime. And we're going to take all of this whole thing, and we're going to call this n. So our equation gets real simple now because everything is kind of compacted. It's almost like a zip file where n unpacks to be this complicated thing and s unpacks to be this complicated thing. But you can see that n is a vector term which includes information about the direction to the planet and also this angle phi. It's all kind of wrapped up in n. So our equation looks like 1 is equal to si prime transpose n. Okay, where, to be clear, this is the factorized and normalized line of sight direction in an image. And then n is some intermediate variable that we would like. Now, you can imagine that in our image, and I'm going to quickly duck back over to lecture 23, we don't just have one point on the horizon of the image, we have several points on the horizon of the image. So it's not unreasonable to assume that we could form this equation several times and stack it. And if we did that, so if we have many horizon points, this is reasonable. If we have many horizon points, we can solve for n in the least square sense. Right? Because we would just have this. We would have S1 prime transpose all the way down to, got to be careful here. I'm going to use the letter M prime transpose. And then this is just going to be the vector n. And then this is going to be a whole bunch of ones. So if we have M horizon points, this matrix that we form is going to be M as in Mike by 3. This is going to be a 3 by 1, and this is going to be Mike by 1. Okay, so it's reasonable to build this matrix, solve in the least square sense for n. Okay, great. So now we're assuming that in our algorithm, in our flight software, we have n. That's not what I asked for. I wanted the position of the planet. So how do we recover r? Okay, so now that we have n, our mission is to recover prime. Right, we're still not assuming we can solve for r. We've got to take care of the r part later, but r prime would be nice. So as a reminder, the sine of phi prime is 1 over norm of r prime. Okay. Also, if you take n and you take the norm of n squared, that is equal to n transpose n. Wow, it's kind of an R looking n. I'm going to try that again. Which is n transpose n, which if you work out the equation is going to be 1 over cosine squared of phi prime. Okay, and also remember that the sine squared of phi prime, this is like the fundamental trig identity, right? Sine squared theta plus cosine squared theta equals 1. So cosine squared phi prime is equal to 1. Okay, that means that the cosine squared of phi prime is 1 minus sine squared of phi prime, which means that n transpose n is equal to, okay, this would be 1 minus 1 over norm of r. Okay, or we could rewrite this as 1 over 1 minus 1 over the norm of r. Oh, sorry, this is prime. Prime, and then squared. Okay, just a fun, actually, there's even one more step we could do here. This is equal to, if you continue to do the algebra, the norm of r prime squared divided by the norm of r prime squared minus 1. Okay, so keep pushing. What do we get? We get that n transpose n times the norm of r prime squared minus 1 is the norm of r prime squared. Okay, keep bearing with me here. N transpose n norm of r prime squared minus n transpose n is equal to the norm of r prime squared, or n transpose n minus 1 times the norm of r prime squared is equal to n transpose n. Okay, so bear with me here. We're pushing n transpose n over to the other side of the equal sign, the r prime squared over to the other side of the equal sign, and we end up with this. Or after some sleight of hand, we get that r prime squared norm is n transpose n over n transpose n minus 1, which we can just square root. So we get that the norm of r prime is the square root of n transpose n over n transpose n minus 1. Okay. Does that answer our question? No, but this is neat, and we're almost there. So we can see how we set up this equation, which I guess this will be equation 3 star. We set up equation triple star with information in our image, and we solve for n. And now we know that from n, we can recover the norm of r prime. We're still not quite there. We've made some good headway. We originally defined that n is just r prime divided by the norm of r prime and then cosine of phi prime. Okay. By that same merit, right? Cosine of phi prime is a scalar. The norm of r prime is a scalar. We know that n and r prime point in the same direction. They're literally the same vector, just scaled differently. So by that same token, n over the norm of n is r prime, oops, not normalized, and r prime over the norm of r prime. Or we could say that r prime is the norm of r prime n over the norm of n. And now we can make a substitution. That is equal to, didn't we just say that the norm of r prime is all this stuff over here? So I'm going to say that we have this going on. It's n transpose n over n transpose n minus 1 square root, and then we still have 1 over the square root n transpose n and n. Which, if we do a little bit of algebraic manipulation, we'll find that r prime, which is what we're after, is n over square root n transpose n minus 1. And that's it. So for now, all the dominoes are in place, because remember that RC prime is just BRC, and RC is what we're really after. So this means that RC is B inverse RC prime. But we just said that R prime is this n over square root n transpose n minus 1. So that means that the actual answer to our question, the position of the planet in the camera frame, is the matrix B inverse the vector n over square root n transpose n minus 1. Okay? And we can make it even easier. We said, remember also that B is just D, which is a modified form of the planet shape matrix, and our rotation, camera to planet. Let me make sure I didn't get that backwards. It is, yep, camera to planet. Okay, so B is just D times T camera to planet. So then by that same logic, B inverse is D TCP inverse, which is TP to C D inverse, where DP to C, I mean, that's just the transpose of T, C to P. So we're assuming that we know our camera attitude before we start this problem. That was kind of baked in. And D inverse is the easiest form of the planet shape matrix. It's literally just A, B, C along the diagonal. And that's it. So we can combine everything to our final equation. Get ready. We have RC is N transpose N minus 1 to the negative 1/2 power. And then direction cosine matrix from planet to camera frame, D inverse N. That is it. I'm going to draw a box around this one. And this is our horizon-based OpNav solution. And so before I shut up for a minute and say any questions, let me just summarize everything, because I realize that we've been doing this for 2 whole lectures here. So the whole procedure is going to look like this. You will be given, or we'll just say for now, given UI. So this is a centroid, not a centroid, because I'm thinking of Starfield images, sorry. Given points in the image, several of them, where I goes from 1 to M. And those points are, per our diagram in the last image, those are points on the lit limb of a planet. And we're also assuming that we know the rotation from the camera to the planet frame. And we're also assuming that we know A and B and C, which are the camera, or sorry, not the camera, wow. The planet long axis, short axis, and medium axis, right? Planet shape parameters. If we know these things, then number 1, we will compute. Actually, maybe compute isn't quite the right word. I'm just going to say form. Do we need both of these? Yeah, I guess we do. D, which is 1 over A, 1 over B, 1 over C, 0, 0, 0, 0, 0, 0. And D inverse, which is even easier, it's just A, B, C, 0, 0, 0, 0, 0, 0. Done. Okay. Step 2 is compute horizon points in the image plane. And this would be undistorted. Okay, and we'll get this in the form of xi hat, where these are homogeneous coordinates. I'm going to try one more time to make the letter S. Sorry about that. That'll do. All right, next is we compute this Si prime, which is what? Well, it's d t from C to P, xi hat, and then normalized. So I put the bracket around there to say divided by its own norm. Right? Then we'll say we will form the matrix. I'm going to call it H, for lack of a better term. And this is going to be S1 prime transpose all the way to SM prime transpose. There's going to be a 3M by, or sorry, what do we say it was? It was a M by 3 matrix, where M is the number of our measurements. And then number 5 will be solve Hn is equal to a vector of 1s using least squares to find n. And then finally, step 6 is RC is n transpose n minus 1 to the negative 1/2 power t from p to c d inverse n. And we're done. And I will say one final note. Well, I guess 2 things to be careful of. So be careful. As defined, all the way back when we set up this problem, RC is the vector from the camera to the target, like the Earth or the Moon. So this is actually the negative of your position. So if on homework 6, you give me a position with a minus sign in front of it, I'm going to take like a point off just to be a snot. But yeah, we want to make sure that we get this right. RC is the vector from the camera to the target. So your real position is the negative of this. And the other be careful, which we didn't really talk about, is we use what are called limb points in the image. So I've completely left out how to do the image processing for horizon-based OpNav, which turns out to be the hard part. However, on homework 6, it's fine if we want to take a shortcut. We'll talk about that, out of the recording. But for now, the point that I want to get across here is this. So imagine that you have an image. Looks like this. And then imagine that you've got a, crescent, Earth, or Moon in the image. Then you're going to have 2 lines here, where this line is going to be the planet space line, which is sharp. You can imagine 1 pixel, you're looking at the moon, the next pixel, you're looking at space. Nice, sharp line. And this is called the limb. Over here, we have the day-night line. So we have this kind of fuzzy, smooth transition from the bright side of the moon to the dark side of the moon. So this is going to be kind of fuzzy. And this is what's referred to as the terminator, where the terminator is not a killer robot sent back in time to get Sarah Connor. The terminator is just the day-night line on the moon or the Earth. We don't use that because you can see how if we're getting points, I mean, if you just kind of blindly looked for the edges of the Earth in the image, you'd get some limb points and some terminator points. But the terminator points are useless for us because what we want to do, if we go back up to the top of lecture 23, we're clearly looking for these points, right? The limb points, where we can fit the entire shape of the planet to those, even if we lose information about the other side of the planet. And in general, we will. It's rare to get kind of a full moon or a full Earth optical navigation image. Generally, we get like a crescent or a gibbous shape, and we just use the nice sharp limb side rather than the terminator side. And that's about it. That is everything that you'll need for homework 6. We can discuss the other gory image processing details later, but I think that's enough for now. Any horizon-based OpNav questions? All right, excellent. So I'm going to stop the recording. I have a few thoughts on homework 6 that I'll share with you, but no reason to bother everybody else with that. And if you're interested in taking off, you're certainly welcome to go anytime you like. The rest of this is just kind of FYI.